Hi, everyone. This is the first lecture for Physics 223. The class this summer will be done asynchronously. So I'm going to record lectures and then have office hours where you can come and ask questions. But I'm not going to require you to actually be online using Zoom at any particular time. Just if you have questions, you can come talk to me during the Zoom sessions, office hours that are listed in the syllabus that's posted on the Canvas page. So most of the stuff you'll actually see on Canvas. There right now should be a homework assignment and a reading quiz. In the lab section for Canvas, you'll soon see the lab posted there. So check out the syllabus. If you have questions, let me know via email or via one of the Zoom meetings that is scheduled as an office hour this week. For right now, I want to talk about the first subject a little bit. So there will probably be a few lectures from chapter 15. Now this textbook I'm using this term is the OpenStax University Physics textbook. We're going to start in volume 1, chapter 15, and then we'll be going to volume 3, just because the material is spread out. But they are free to be downloaded. I believe you can buy or purchase a hard copy as well. But they're free to be downloaded at the OpenStax website. You should find the link in the syllabus for that. So let's start talking about chapter 15. And chapter 15 has to do with oscillations. And the first thing to describe about an oscillation is the period and the frequency. So by an oscillation, I just mean a motion that repeats itself. So it could be like a pendulum, swinging back and forth, for example. The time for one cycle, one oscillation to go all the way back and go out and back to where it started from, we call the period. And I'm going to denote that by a capital T. Now, usually, though, much of the time we talk about the frequency of the oscillation, which is the number of oscillations per second. Now, if you think about it a little bit, you can see that the frequency and the period are inversely related to one another. That is, the frequency is 1 over the period, or the period is 1 over the frequency. Right, if you had a period of 1/4 of a second, 0.25 seconds, the frequency would be 4 cycles per second. Now, the unit that's usually used for frequency is the hertz, denoted by Hz, and it just means cycles per second. But often we'll talk about angular frequency, which is the number of radians per second. And we can usually relate a repeating motion to kind of a circular motion, right? Going all the way around through 2 pi radians or 360 degrees. But if we want the angular frequency in radians per second, we just multiply the frequency in hertz times 2 pi. Again, using this inverse relation, angular frequency is 2 pi over the period. So that's kind of the number of radians per second. All right, so if you went through 4 pi radians per second, that would mean you had a frequency of 2 hertz. You're making 2 complete cycles per second. So one of the prototypical situations that we'll end up talking about in this chapter is a mass connected to a spring. And this is going to be an example of what I call simple harmonic motion, and I'll describe why I call it that in a moment. But the mass on the spring, we have it connected. If we stretch the spring from its equilibrium, where it normally wants to be, we're going to call that amount of stretch x. Now, x can be positive or it can be negative if I compress the spring and I'm pushing it in. X equals 0 at the equilibrium point. The force law describing the restoring force, I call it a restoring force because the spring always wants to pull the spring back to equilibrium, pull or push. But the force law describing that is called Hooke's law. Turns out the force is proportional to that displacement of the mass. And K, I call the spring force constant. Now, the negative sign here just tells me, right, it's always trying to go back to equilibrium. If I were to compress the spring, I'd have a negative x. Multiplying by another negative, I'd have a positive x, which makes sense. It's pushing it back in the positive direction. So the main goal here right now, what I want to do is figure out the motion of this mass connected to a spring. As you know, it's going to oscillate. There's going to be a frequency and a period associated with it. But I could also describe x as a function of time. Where is that mass as a function of time? Now, if I know x as a function of time, I could also get the velocity as a function of time, v of t, just by taking the derivative, or the acceleration by taking the second derivative. So how do we do this? How do we determine x? Anytime we know the forces, we go back to physics 221 and we apply Newton's second law, right? Which says that if I add up the forces on something, it has to equal the mass of that something times its acceleration. Again, acceleration is the second derivative with respect to x, the position. So I'm just going to plug in our Hooke's law, our force law, negative kx equals mv squared x dt squared, the acceleration. Now, this is different than what we did in physics 221. We usually dealt with constant forces. So you could easily just solve for a, right? A would be like negative kx over m, and you'd have a constant acceleration. In this case, though, the acceleration is changing, and so is the velocity as a function of time. So this is a differential equation. We have to solve this. Now, if you've taken a differential equations class, you'll often see different methods of solving types of equations like these. One way to do it, though, is to just make a guess. And if you look at this, you can see that, well, if I take a second derivative, I've got to have the same function back, maybe multiplied by a constant, but negative, so they add up to 0. And if you think about it a little bit more, there are a couple functions that would make sense, and cosine and sine, right, they repeat. So I might guess the solution has the form like this. X as a function of time equals a constant, times cosine of omega t plus phi, another constant. Now, there are two constants here, a and phi. They will depend on how the motion started, or the initial conditions, and I'll do an example of that in a moment. Now the omega here, the W, sometimes we call it W, I defined on the last page, the angular frequency, it's actually the Greek letter omega, multiplies by the time, right? Because it's going to be radians per second times seconds will give me the radians. And sometimes this whole argument of the cosine is called the phase, or the phase angle. Now, I may want to prove that this is a solution. Well, one way to do it is to take my derivatives, right? Well, if I take the first derivative, I get the velocity. It's negative angular frequency times a sine of omega t plus phi. Right? Just take the derivative of the cosine, I get a sine. Chain rule pulls out that negative omega. Take a second derivative to get the acceleration, I get negative omega squared a cosine of omega t plus phi. So what I can do is plug this in to my Newton's second law equation for the second derivative, and this in for x, and I get this. Now, when you do this, you'll see all these a cosines cancel out, and I get negative m omega squared equals negative k, or if I solve that, omega equals square root of k over m. This tells me what the actual angular frequency is, and it only depends on the spring constant, how stiff the spring is, and the mass of the spring. Sometimes we call this the natural frequency. If we let go of the spring, it will oscillate at that frequency. And it comes directly from Newton's second law, from getting the solution. So what I have shown here is that the solution for a mass connected to a spring is a cosine. Now it could be a sine, right? I mean, sine and cosine are the same, they're just shifted from one another. And the natural angular frequency is the square root of k over m. Now let's talk about the constants a little bit. A, we call the amplitude. It's going to tell me the biggest value of x, right? The furthest the spring gets out from the x equals 0, and the furthest it goes back. A can be positive or negative. It oscillates back and forth between the positive and negative amplitude. Now phi is the starting angle. What is the angle when t is equal to 0? Right? It tells me how the motion starts. And in fact, any differential equation that's second order in the derivative, two derivatives, will have two constants that depend on how the motion started or the initial conditions at time equal to 0. So let's do an example here. Let's say I've got my spring and I've calculated omega, depending on K and M, be 5 radians per second. Now I start the motion at the equilibrium. At x at time equal to 0 is 0 meters. So it's just sitting there, it's not moving. And then I give it a push and give it an initial velocity at that initial time of 0 of 2 meters per second. How do I determine these two constants, amplitude and initial phase? Well, I just use my solution and set time equal to 0, right? So x at time equal to 0 is just a cosine of phi. Now, if this is 0, well, the only way to get or satisfy that condition is that if the angle is actually pi over 2, right? Because cosine has to give me the 0. A is never 0, it's the amplitude. So cosine of pi over 2 is 0. Now it could be 3 pi over 2 or 5 pi, but I'm going to choose the simplest one. So actually I made a mistake here. It should be pi over 2. Maybe you can see that what if the initial phase were 0? Well, the cosine of 0 is 1, so this would mean the motion started at the amplitude. But in our case, the phase is pi over 2, satisfying that first initial condition. Now the second initial condition will give me the amplitude here. If I take my derivative, my velocity, remember it was negative omega a sine of omega t plus phi. Now t is 0, so I get sine of phi. Now phi is pi over 2, which gives me 1. Sine of 90 degrees or pi over 2 is equal to 1, right? So v at time equal to 0, my 2 meters per second, is equal to 5 radians per second omega times a. I can solve for a, and I get 0.4 meters. So the main point here is that I've got my solution for any motion of a spring, and I call this simple harmonic motion because it's like a cosine or a sine. You can have more complicated oscillations, but they will not be described by a cosine or a sine function. We'll maybe be talking about an example of that in the next lecture. But again, this is my solution. To determine the constants, I use the initial conditions. So in the homework, there will be some questions about this. You might be given the constants and have to figure out what the frequency is, or you could be given the initial conditions and have to determine those constants. In the next lecture, I'll talk about another example of simple harmonic motion, the simple pendulum, and we'll talk about another way of kind of relating the amplitude and the velocity through conservation of energy.